Bismillah ar-Rahman ar-Rahim. In the previous lecture, we started the design procedure for sequential circuits. Okay, and we said that basically the design procedure starts with the problem description or verbal description of the problem. Okay, and then this is followed by derivation of the state diagram, and then we do the state assignment. Then we derive a 2D state table and then use K-map to find the next state equations, and the output equations. And then we finally draw the circuit or the logic circuit, okay? And then we took an example, all right, that is basically a sequence detector that detects the sequence 101. And this sequence, by the way, is an example sequence, okay? It's an example sequence. In the exam or in quizzes, you may get different sequence, okay? And your circuit will be different, all right? So understand how we get this state diagram and then generalize to any other sequence, okay? So we got the sequence like last time in here, okay? So basically what you should do, okay, is to follow the path in which the circuit will detect the sequence. Okay, so you start with SI, initial state, okay, and then get a 1, output is 0, and then a 0 where the output is 0, and then a 1 where the output is 1. Okay, you have to figure out to which state you go next. Okay, this depends whether the overlapping is allowed or not. Okay, if overlapping is allowed, then you can use whatever part from the previous sequence to be part of your new detection, okay, new detected sequence. For example, here in the example, in this example, we have 1, 0, 1, and then followed by a 0, 1. So this sequence here and this sequence here share this 1 here. If overlapping is not allowed, then we wouldn't drive the output high here, okay? So overlapping makes us drive the output high whenever we observe the sequence, even with overlapping. Okay, so this is a Mealy machine, and then once you finish deriving the detection path, you start with the other alternatives. So here, this is when you receive a 1, you go here. But what about when you receive a 0? Here, when you receive a 0, you go here. What about when you receive a 1? And here, when you receive a 1, you go here. What about when you receive a 0? Okay, so think where to go next, keeping in your mind that overlapping is allowed. So which state do we go next? And what do you think the previous inputs, okay, gets us to which state? Okay, after deriving the state diagram, okay, we do the state assignment. And we said last time that having 3 states, okay, means that you need 2-bit for that, okay, at least 2-bit. And 2-bit allow you to encode 4 states, not just 3. Okay, so you have 0, 0, 0, 1, 1, 0, and 1, 1. So you just choose 3, any 3 from this range, okay, to assign it to one of your domain or states, okay? So in general, you have SI have 4 possibilities, then S1 have 3 remaining possibilities, and then S10 will have 2 remaining possibilities. So if you multiply them out, you get 24 possible assignments. Okay, you have 24 possible assignments, and each assignment will result in a different circuit eventually. Okay, so one of the problems of the Mealy machine, okay, is what we call the false output or glitches in the output. So suppose that we are in this state here, S10, And then we can have a 1 or a 0, right? If we have a 0, then the output will be 0. If we have a 1, then the output will be 1. Suppose that the input here, when we are in S10, changes briefly to 1, like this, I'm sorry, yeah, and then goes back to 0 before the rising edge of the clock. Okay? So since we are in S10 and we receive a 1 for even a brief period of time, then the output will be 1. So I have my Y goes 1 here. Okay? But then my input changes from 1 to 0, so my output changes from 1 to 0 as well. Okay? So the output goes 0 once X goes 0. Okay? So we call this a false output or a glitch. Okay, so this is a false output or a glitch, and this is one of the disadvantages of using a Mealy machine. However, the advantage of using Mealy machine is that it results usually in lesser number of states than Moore machine. Okay, we will after we finish this example, we'll be deriving the Moore machine for the same problem. Okay, and you will see that it requires one more state for the Moore type state diagram. Okay, but keep in mind that in Mealy machine we get what we call a glitch. Sometimes we get a false output that the sequence is detected, but it's not. In fact, it's not detected. Okay.
Doctor, can you
Yes.
please?
Question.
Yes, I don't understand. Is this a hardware problem, the false glitch output?
No, it's not a hardware problem actually, but we expect, because we expect the input to be either 1 or 0 here. We are in here, okay? We are in here. And we expect the input to be 1 or 0, not both. It does not switch during the same clock cycle, okay? But for some reason, our input glitched, okay? For example, it glitched. Okay, the input is supposed to be a 0, okay? But it has a spike, okay? And then it became a 1 for a short period of time, okay? Then
Yes.
this glitch here in the input will affect the output as well. Output will become a 1 because of this glitch, okay? So normally the input will not change during the whole period. It will change during the beginning of the period, but not during the period, okay? But you may get some glitches in the input, some spikes, okay? And these glitches will affect the output, okay? It will affect the output to get glitches or false outputs as well. Do you get it?
Yes, yes. Now I get it.
Okay. All
Thank you.
right. Now, the next step is to derive the what we call the 2D state table, and I have copied the state diagram and also the state assignment in here. And we have, this is the present state here, present state, where we have state A and state B, okay? And we use the state assignment to be SI to be 0, 0, and S1 to be 0, 1, and S10 to be 1, 0, okay? So this is SI, S1, S10, okay? And this state is not used here. So what we do, we have don't cares here, but since we may end up inside this state, inside 1, 1, okay? Then we would like to be able to initialize our circuit to go to the initial state, okay? If in case, just in case you turn up your circuit and you go to state 1, 1, okay, then we would like the circuit to go to state 0, 0, regardless of the input, okay? And then the output will be also, we want the output to be 0, 0. So the state will reset automatically to the reset state, okay, in case we go to state 1, 1. Okay, now we got the state diagram last time, okay? I mean the state table. Now it's time to derive the functions for A plus and B plus and Y. This is nothing but a truth table in disguise, right, guys? It's a truth table in disguise. And we can take advantage of K-map uh, because my K-map for three variables. Now I have three variables, like I have the present state, which is 2-bit, and the input, which is 1-bit. So I have 3-bit as my input. Okay, so I have to have a 3 input K-map, but I want my K-map to match the shape of for example, the output, and the shape of the input of the next state, and the shape of the other next state. Okay, so I want my K-map to be like this. So this is my X now. My X can be either a 0 or a 1, right? And my AB okay can be 0 0 0 1 1 1 and then 1 0. Okay, 1 0. Okay, let's do the output first. Okay, the output first. Where is the one in the K map for the output? So this is my output here. Where is this one here? Which row and which column?
One zero. AB 10 and
X.
X 1.
Okay, so all right. So which row and which column?
Row number 2. Column, the last column. I think.
أيوة. And
لا column number 2, the last row.
excellent. Yeah. Just make sure that you don't do it this way. Okay, it's not this. This is wrong. Okay, it's this one, because we have 1 1 0 1, and this is 1 0 1. Okay, you see that? Okay, so this is nothing but a minterm. Okay, so my y is nothing but a minterm. So my y is going to be minterm number 5, which is a b complement x. Okay, what about a plus now? A plus is the input of my first flip-flop. This is a plus. This is one column of a plus, and this is the second column of a plus for x equals 0 and for x equals 1, right? So I can, in fact, copy this K-map and reuse it for a plus once and b plus once. Okay, but I need to erase this one. Okay, so for a plus, it is what? When is it 1 for a plus? This is a plus. Who can tell me which row and which column the K-map is 1 for a plus?
Row number 2, column the second
Number,
column.
excellent. Yes, it is 0 0 1 0 1 0, right? 0 1 0. This is the only one. So this is the only one for a plus. So it is again a min term as well. So my a plus is equal to what? A complement b what? X. Right.
Doctor, why we put the x equals to 1?
Okay.
Here and
It is 0. In fact, yes, you're right. Excellent. So somebody is paying attention here. Okay. So it is 0. Yes. So so 0 1 0 0. Okay. This is 1. So my 1 here is here, not here. So the only difference is x complement. Okay. You get that?
yes.
All right. Now you tell me where are the ones for B plus?
First row, second row, third row, second column.
Second column, first row, second row, and third
Third
row.
fourth row.
Yeah, okay. Excellent.
1-0, yes.
Yes. This is confusing. You may forget this during the exam and then you get the whole thing wrong. So please pay attention not to do this mistake. And to do the grouping here, you just take the top two together and the bottom two together. Okay, and this is my A and my B. Right? Both of them will have X, true value of X. So B plus will be equal to A complement X ORed with what? B complement X. Okay? Now you have your next state, which is the flip-flop input. Okay, and you have your output, right? So all you have to do is to draw the two flip-flops, D and then the clock. I'm assuming a positive edge triggered flip-flop. And this is my Q, and this is my so this is my flip-flop A. Let me just copy this and then paste it and then label it separately. Okay, so I have, this is my flip-flop A and this is my flip-flop B, excuse me. So the output here is A and here it is a complement, okay? Remember that the flip-flop outputs for us Q and Q complement, okay? And this is my B. I'm labeling the nets because I want to use them instead of connecting them in a feedback fashion. I'm going to use the same net name, okay, without connecting them physically. But if you use the same net name, then it means that they are the same wire or the same net, okay? So for A, okay, it is A plus here, which is this input here, A plus. The next input, the next state input for A is A complement, B X complement, okay? A complement, so we have a three input AND gate here. A complement, where do I get this from? I get it from here, right? I just have a wire here and connect it with this one, okay? But I don't have to show it here, okay? And then B, and then X complement, okay? For the next one, we have an OR gate, fact, that is feeding the B plus, and then two input AND gates. One is having A complement X, and the other is having B complement X, okay? All right. Are we done?
We have to find the output.
Excellent. Yeah, the output. Output is a three input AND gate. So we have A, and we have B complement, and we have X, okay? And this gives me Y. Are we done?
Yes.
There is an important thing that we missed here, which
Is
is
the clock?
the clock. Excellent. Yes. So the clock must be annotated. Okay. Otherwise, your flip-flops will not work. Okay. You have to connect the clock input to the same clock. They have to be synchronized by the same clock. Okay. Both of your states, both of your state variables have to be synchronized with the same clock. Otherwise, your assumptions will not work as expected. Okay. Are we done? I'm going to go back to okay, it's here actually. Look at the state diagram and tell me if we are done or not. I'm going to give you a hint. Huh? شباب.
Yes, we
You
need
have
to
to
reset.
take the output to the input again.
You have to take the output to the input. What does that mean? You mean connecting the like this? You mean this one here taking a complement to A? No, this is perfectly fine. It's understood that this net and this net are the same. It's perfectly understood, and it's neater, even neater. Okay, I prefer to see it this way rather than connecting it backwards, because if you connect it, it will look ugly and it will be very difficult to trace. Okay, so this is not the thing that we're looking for. Anyone, any suggestion here? Okay, so the thing that I was hinting you here is the reset state. Okay, we must have a reset button to go to the reset state. So we have an asynchronous reset input for the two flip-flops, in which when asserted high, okay, when reset is high signal, I should go to state 00. Okay, 00. This because it works like this because I have assigned my S initial state 00. If I assign my state initial to be 01, then you cannot have this. You must have a set, an asynchronous set, an asynchronous reset. Okay, and you must connect both to reset. All right. So reset logic is important as well. Okay, so this is the only difference here is that it is an asynchronous, so it doesn't depend on the clock. Whenever this is 1, the content of the memory will be reset to 0. Okay. Okay, any question here? All right, so now we are going to, I'm not going to go over the whole problem, okay, but I'm going to derive a Moore type state diagram that detects the same sequence, with allowing overlap. Okay, so if you think of Moore machine, what does it mean? Means that the output is a function of the present state. Okay, the output is a function of the present state only. Okay, so this implies that this problem here is never going to happen. Why? Because even if my input has some spikes, my output is a function of a stable state. Okay, it's a stable state. Okay, so the output is going to be stable during the whole period in which you are in one of the states. Okay, so there is no what we call false output for the Moore machine. Okay, this is something that is preferable about Moore machines. Okay, even though they result in more states, as we will see. So let's start our Moore machine. We have the initial state. Okay, and our output is 0 here. Okay, because remember, in the Moore machine, the output is a function of the present state only. So we draw the output inside of the state, indicating that it is not a function of the input. Okay, so again, if I receive a 0, 0 is not part of my sequence, so I should stay in SI. However, if I receive part of the sequence, then I should advance my search. So part of the sequence is when I receive a 1. Okay, and in this case, I'm going to S1, and still my output is 0. Okay, but I know that I received 1, which is part of my sequence. Now, if I receive another 1, same thing happens here. Okay, I should loop back to S1. And if I receive a 0, I should advance my search. S10, and the output is still 0. Okay. Now here, the interesting thing happens. Okay. If I receive a 1 now, what happens? I should go to a new state. S101. Okay. And in here, this is my sequence and it is detected now. So I should output a 1. You see that? Is this clear? This is if I receive a 1.
Yes.
Okay. Now, what happens if I am here and I receive a 0? It's actually by the same reasoning, I should go back to the initial state because I ruined the whole sequence now. I should go back and search from the beginning. So this is if I receive a 0. Okay? But now this is finished. This state here is covered, 0 and 1. Okay? This one now is remaining. Excuse me. If I receive a 1 here, sorry, I receive a 1 here, where do I go? So I have already 101, and I receive a 1. This is my new input now. Where do I go? What is it?
S1.
Excellent. Yeah, S1. This is 1. If I am in S101 and I receive a 0, where do I go?
Stay.
The same?
Stay.
Stay in S101? You mean the output, since I got 010, I should get what? I should get a 1 as well?
I'm sorry. It's S10.
Yeah, so you go back to, this is part of my sequence, right? So you
Yes.
go to S10 if you receive a 0. Is this clear? It's important that this is clear, guys. This is because we are allowing overlapping now. We're allowing overlapping. If we don't allow overlapping, the things will be different. Okay? All right. So I'm not going, so the only thing that is remaining is to annotate the reset state. Reset. Okay? So by this, I'm not going to derive or implement the circuit, okay, for you. Let's leave it as an exercise to you to do the state assignment and then do the 2D state table, K-maps, and then draw the logic circuit, okay? Try it for 1 or 2 assignments and see that, just convince yourself that you'll get different hardware each time, okay? All right. Now, we covered what we call sequence detection. So you should be able to answer to if I change the sequence, you should be able to derive either a Mealy or a Moore machine for the same sequence. How many states does it take to detect 3 bits, a sequence of 3 bits in Moore machine? 4, right? Just counted them. Okay, 4 states. How many states do we need, okay, if we want to detect an n-bit sequence using a Moore machine? It's going to be n
plus 1.
Yes, n plus 1. What about Mealy?
N. Only N.
N. It's n. It's not n plus 1, okay?
Yes.
All right. This was an exam question, by the way. Previous term. Okay. Now, we are going to talk about what we call code detection, okay? Code detectors, okay? Let me just make sure that these are read as 2 words here, okay? Okay. Okay, so code detection and sequence detection are different circuits. Okay, the code is a fixed length, let's say message. Okay, fixed length message. So you have to tell me the length of the code. For here, for example, I'm telling you it's a 4-bit code. Okay, so what happens is that you are receiving the code serially through an input X, for example, and then deciding whether you receive the code that you're looking for or not. Okay, so when do you get your output? You get it after receiving the final
Yes.
bit of the code. Okay, final bit of the code. All right, so code is different from a sequence in the sense that we need to know how many bits have we received so far, and we need to know that we received a 1 in the 3rd position, a 1 in the 2nd position, and a 0 in the 1st position, and a 1 in the 0th position. Okay, so it has to be to respect positions as well. Okay, so now let's start with this. So I have the initial sequence, initial state. Okay, now let's start with the other alternative. Now I know that my sequence starts with what? With a 1, right? My code starts with a 1. So if I get a 0, then my output will be 0, right? And what? I go to S0, all right? Now, all I need to do is to wait until my code here is over and then go back to the initial state. And I know from this place here, actually, that my final output will be 0. Why? Because it is impossible when you receive a 0 at the beginning, it is impossible that the code will match. Okay? All right. So no matter what you get after this, it's a don't care, and the output is still 0. All right? So whether it's a 0 or a 1, the input is a 0 or a 1, then you'll go to a state S0X. Okay? And then no matter what you get after as well, okay, then you'll go to state what? 0S0XX, right? And then you receive your 4th bit now, which is the final bit of the sequence. Okay, the final bit of the sequence. And after receiving the final bit of the sequence, you should go back and look for the sequence or the code again. Okay, do you get that? So this is X, and this is your final output. Okay, this is your final output for the code that you did not detect. Okay, now you look for the code again. Okay, in the next code that you receive. Now, if you're lucky, you'll get a 1 here. 1, but the output is still 0. Maybe this is not my code. Okay? And then I go to S1. All right? However, my code is what? My code is 11. My code is 1101. Okay? So if I receive if I receive a 1, then I should advance my search. Okay, 1, but still the output is 0. We don't know what we receive next. Okay, so this is S11. All right, and if I receive a 0, then I'm lucky. Okay, the output is 0, and my state is going to be S what? 110. And if I'm super lucky, then I should receive a 1 here. Okay, a 1, and then I go back again and look for another code. Okay, but my output here is 1. Do you see that? Okay.
Doctor,
Yes.
when we receive 0 at SI, why we have to look for S0 and S0 X.
Because my code is 4-bit. I have to
So
wait.
I have to move 4 bits and look again.
Yes, exactly.
Ah.
This is the difference between a code and a sequence. Sequence is a variable length, but the code is a fixed length. I have to know which bit I'm looking for, okay? I have to know where am I in the code here, okay? So this keeps track of which bit I'm processing, okay? If I'm in here, then I'll be processing the first bit. If I'm in here, then I'm processing next the second bit, and so on and so forth. Do you see that?
Yes, it's clear.
Okay. Now, let's start with, let's do the alternatives for this path now. Okay. Now this one is check, okay, except for the probably the reset. I need to annotate the reset. Okay. However, still here we haven't covered all the outputs, all the outcoming arrows, and here we haven't covered all the outcoming, and here also we haven't covered all the outcoming. So here, let's start with this one. Here we covered the one. What if we receive a 0?
It will go back to initial and output 0. Yes.
Excellent. So I have a comma here, 0, comma 0, 0/0. Okay. Did you get that?
Yes.
Okay. Next, let's just backtrack from here to here now. And here, if I'm lucky, I'll receive a 0. However, if I receive a 1, then what happens? My sequence is ruined, right? Then I should go where?
To the left side.
To the left side. Which state?
S0X. Sorry, S0XX.
Excellent, because I have only one input to process and then move to the initial state. So this is if I receive a 1, is it? Yeah, a 1. Okay, and then output will be 0. Okay. What if I am in S1 and I receive a 0? Where do I go?
It will go to S0X.
Excellent. Yes, S0. So I receive a 0, the output will be 0. You see that? Because I need to know where am I in the sequence, in the code, whether I'm in bit 3, bit 2. So the key thing that you need to know is that if you measure any loop starting from SI and coming back to SI, it must cover 4 states only. So here, this is 4. Here, for example, it's 4. Here, it's 4. And here, it's 4. You see that? So no matter what you take, okay, it's always going to be 4 hops, okay? Any question here? All right. No questions are there. Let me go back here, okay, and try the state assignment and then try to solve this, okay? I'm going to solve this up to implementation because we still have time. Okay, let me add the page here. So first of all, I will assign my states the normal binary numbers. So my normal binary assignment, SI is 0, 0, and S1 is 0, 1, and S10 is going to be 10, and S101 is going to be state 11. Okay, because we only need 2 flip-flops. I need to have 2 bits for the assignment. Okay, so now we have to get our what we call 2D state table. Okay, so I have the present state now, and the I think I need to pull this down a little bit. Okay, and the present state, and the next state for x equals 0 and x equals 1. Okay, and the output, do I need to say x equals 0 or x equal 1 for the output? Answer is no. Answer is no. Why? Because this is a Moore machine. Okay? So this is only Y. Okay? And this is what? This is, let's call them A plus and B plus. A plus. Sometimes we call them DA and DB. And this is A and B. Okay? So please pay attention. Pay attention to that so that I do a mistake, you catch it. Okay? So we have 0, 0, 0, 1, 1, 0, 1, 1. Okay? These are the states. Okay? Now, for A plus, okay, if I receive, let's do the output first because it's easy. Okay? The output is always 0 except in state 1, 1, which is 1. Okay? For A plus, or let's say for the next state when X is 0 and the present state is 0, 0, what is the next state? It's 0, 0. Okay? You don't go anywhere. And when X is 1, we go to 0, 1. What about when we are in 1 and we receive a 0, we go to 1, 0 basically. And if we receive a 1, we stay in 0, 1. We are in 1, 0 and we receive a 0, so we go to the initial state now. And if we receive a 1, we go to state 1, 1, right? We are in 1, 1 and we receive a 0, we go to 1, 0, right? If we are in 1, 1 and we receive a 1, we go to 0, 1. So this is more interesting in terms of K-map because you have a number of ones. First of all, my Y will be what? AB, right? Without even doing a K-map. What about my A plus? I'm going to draw the K-map for A plus. And when do we have a 1? 0, 1. This is AB. And this is X, okay? So A plus will have a 1 in here and here, okay? Right? And also
Last row when X is 1.
1, 0, 1. Yeah, excellent. So my A plus will be this and with this, or ORed with this, okay? So my A plus equals what? Equals, it's B X complement ORed with this basically min term, which is A complement, I'm sorry, not A complement, A ANDed with B complement ANDed with X, okay? All right, what about the B plus now? B plus is going to be all ones here, okay? And all 0, 0. So it equals what? Equals X, in fact, okay? Equals X. So my B plus is isn't it?
Yes.
Yeah.
So again, I draw two D flip-flops. The clock. Don't forget the arrow, okay, for the clock, okay? And this is A, this is B, a complement, A, B. B complement, and then my A plus is going to be an OR. And we have two ANDs here, one with B X complement, and the other one is A B complement X. and for B, it's only X. Okay. CLK. CLK. Okay. It's the same clock signal. Okay, you just have the same net, so there is an implied connection between the two nets. And then Y, my Y is A and B, right? Just A and B. This is my Y. All right. So the final thing is the reset. It's a reset. Any question?
Yes, doctor. You mentioned the arrow and the C and the clock. What is it?
Which one?
The
This
diagram.
one. I
doctor.
mean, this triangle here.
Yes.
This differentiate between a flip flop and a latch. Okay, so this arrow is important here, or a triangle. It's not an arrow. Okay, so if you go back to the symbol for the flip flop, yeah, here, AZ, there is an arrow here. So if you differentiate this with the or compare this with the latch is similar. It has the same inputs and outputs. However, there is no arrow here or no triangle here. Okay.
Yes.
So it's important that you draw this arrow. Okay. Otherwise, we will understand that you don't know the symbol for the flip flop. Okay. All right. I think by now I finished my lecture. Okay. Let me stop recording so that it doesn't become too long.